Welcome back to the next section of Chapter 2. In this section, we're going to be looking at transforming linear functions. Transformations are something that we're going to be doing pretty much every single chapter, numerous times, and we will get definitely better at it as the year goes on. This first one's a little bit rough, partly because it's the first time, and partly because lines are really boring, and so you can't necessarily see everything. We'll be looking at it again in section 9 of this chapter with absolute value functions, which makes a little bit more sense, I think, just because you can see some more of what's going on. So, let's look at our learning targets. I can transform linear functions, and I can solve problems involving linear transformations. So, looking at our transformations, these are going to be very similar to the transformations we did last chapter with points, but there are some differences, and those differences can be summed up with everything we do to the x's needs to be backwards. Instead of adding, we're going to subtract. Instead of multiplying, we're going to divide. And so there are some differences, but that will be true for all functions. So let's look at our transformations. Remember, we have translations, stretches and compressions, and reflections. Translations, we add and subtract. Stretches and compressions, we multiply or divide. And reflections, we multiply by -1. Each of these has a horizontal and a vertical component. With translations, a lot of times we'll do both at the same time. So, if we want to go horizontal, if we want to move h units right, g of x is going to be f of x minus h. Remember I said horizontal is going to be backwards. It's not x plus h like it was with points. It's just x minus h. And what this means is we are going to replace all the x's in f of x with x minus h. For vertical, we move it k units up. G of x is just f of x plus k. We're going to add k to the function itself. Notice the difference. This x minus h is inside the parentheses. That means we replace x with it. Here we have f of x, it's the whole thing, and then we add k to it. So it just gets added to the end. Both of these translations will change the y-intercept of a line, but it will not change the slope. We're moving the line from one place to another, the slope will be the same. So we'll end up with a parallel line. So, looking at an equation, let's let f of x equal 2x plus 1. This will be the example that we use for all of these for f of x. Let's move the function 4 units to the right and 3 units down. So 4 units to the right means that h is going to be 4, and 3 units down, well, this is k units up, so wouldn't down just be negative up? So this will be a minus 3. So we have f of x minus 4 minus 3. So we're going to take our f of x function. We have 2 times something plus 1, and we're going to subtract 3 from it. And then that something, that x value, becomes x minus 4. Now we need to distribute the 2 to get 2x minus 8. And then negative 1 minus 3 is just minus 2. So we have 2x minus 8 and minus 2. And negative 8 minus 2 is negative 10. So g of x equals 2x minus 10. And so we can see that, hey, this is a parallel line. Now, couldn't we have just gotten here by moving it down 11? Yes, we could have. We could have also gotten there by moving it horizontally a certain distance. You see, that's why lines are kind of boring, because you can do the same thing using multiple translations to get the same results. So let's look at stretches and compressions. Here we're going to be multiplying or dividing. With horizontal, it'll be backwards. So if we're going to stretch by b, instead of having it be b times x, it'll be 1 over b times x that we have to replace with. So when we stretch by 7, we'll replace all the x's with 1 over 7x. If we're compressing by 1/5, 1 over 1/5, it's just reciprocal. It's going to be 5x. So whatever the stretch factor is, we need to do the reciprocal and then multiply. And remember, the difference between a stretch and a compression is what is the number you're using. If you're using something bigger than 1, it's a stretch. If you're using something less than 1 but bigger than 0, it's a compression. But when we flip it, it actually switches places. So if we look at an equation, we see it's a 1/2 x. That's actually a stretch of 2. So again, the horizontal is a bit backwards, but it'll be consistent throughout the rest of everything that we do. So let's look at an example of this one. Let's stretch our function horizontally by a factor of 2. So 2 will go in here for b. So we'll have f of 1/2 x. And that just means we're going to take our function 2 times something plus 1, and we're going to replace that something with 1/2 x. Then we just need to multiply these guys. 2 times 1/2 is just x plus 1. Notice that a horizontal stretch or compression changes the slope. It does not change the y-intercept, though. Because you're stretching away from or compressing towards the y-axis, the y-intercept will stay the same. Let's look at another one. Compress it horizontally by a factor of 1/3. So when we plug in 1/3 here, it's just reciprocal. So the reciprocal of 1/3 is 3. So g of x will equal f of 3x. So take our function, 2 times something plus 1, plug in 3x for the something, and we end up with 6x plus 1. So that's horizontal. Vertical, we're going to multiply, but vertical we do exactly what we think we should do. So if we're going to stretch by a factor of a, we're just going to multiply the function by a. We're going to have a times our f of x. In this case, it'll be whatever a value is times 2x plus 1. So let's stretch it vertically by a factor of 2. So we have g of x equals 2 times f of x, which will be 2 times 2x plus 1. Now we just need to distribute 4x plus 2. Notice the vertical stretches and compressions will change the x value, or the slope, and the y-intercept. It will leave the x-intercept the same, but we don't see the x-intercept in our equation, so it's tougher to see that. How about we compress it vertically by a factor of 1/3? Same thing. We'll just have 1/3 times f of x, which is 2x plus 1. Distribute the 1/3. We get 2/3 x plus 1/3. And so with the vertical, we just have to make sure we distribute to everything. Reflections. We make things negative. That's all it is. It's either we make the x value negative for horizontal, or we make the whole function negative for vertical. And so, for horizontal, the trick to these, remember, is the wording of it. It won't say do a horizontal reflection. It'll say reflect across the y-axis. Now we see y-axis, we think vertical. No, remember, reflections are perpendicular to the axis. So that'll be a horizontal. And then vertical will be across the x-axis. And so horizontal, we will change the sign on the x, so we'll replace all the x's with negative x. So if we reflect across the y-axis of this one, it's just f of negative x. And so we take our function, 2 times something plus 1, and replace the something with negative x. Multiply 2 times negative x is negative 2x plus 1. Again, notice changes the slope, does not change the y-intercept, just like a horizontal stretch. Stretches and compressions and reflections mathematically are basically the same. It's just the reflection is negative. So vertical, it'll be just g of x equals negative f of x. So reflecting across the x-axis, it'll be negative f of x, which is negative 2x plus 1, which means we need to distribute to get negative 2x minus 1. Notice these are very similar, but not quite the same. They have different y-intercepts. And so those are the transformations that we're using. It looks like a lot. The cool thing is we're going to be doing this over and over and over and over again, and everything above that line will be the same every single time we do it. Those are the rules. Everything below the line is just the example with a linear function. We could do this with x squared. If I wanted to move x squared 4 units right and 3 units down, this would still be the same. We would just have x minus 4 squared minus 3. And the same with everything else. So when we see it again and again and again, it just helps reinforce that it's the exact same thing. And we can do transformations to any kind of function we want after just a couple chapters. So enjoy the work, and I'll see you in class.